Hi everyone, today I'm going to be going over the practice problems from chapter 15 in Solomons. So the first question, which of the following structures contributes to the resonance hybrid of intermediate formed when acetate annulid undergoes parabromination? So when I see a practice problem like that, the first thing I think is you're going to need to know your resonance structures for electrophilic aromatic substitution. So let's talk about that. If you have something already substituted, we're just going to call this an R group. And then it undergoes electrophilic aromatic substitution to substitute out a hydrogen somewhere on this ring for something else. The first step is going to be form an electrophile. That electrophile can be attacked and add on either here at the para, meta, or ortho positions. Those are your options. Okay, let's look at each one of these. So if you have something and an electrophile is added at the ortho position, the electrophile attacks, and you end up with actually the electrophile doesn't attack, the benzene attacks. Just got that flipped. You end up with a carbocation. Now this carbocation is going to undergo some resonance structures. First, your double bond is going to move over. This is known as the rhenium ion, by the way. So we've just moved one bond over. Then another bond will move over to fill in the gap of electrons left behind. So we still got our R group, we've got our electrophile and the carbocation. Because this moves over, there's an absence of electrons. That's why the carbocation moves. It's not really so much the carbocation is moving, but the electrons are moving. And because the electrons are moving, a carbocation is left behind. So these are the three possible positions as carbocation. If we moved this double bond over, that wouldn't really make sense. You couldn't fill in that carbocation. And then the proton that's also here is going to be abstracted. The electrons are going to fill in and you'll restore aromaticity. But this right here is the rate determining step. This is the slow step. So you can see in this position, the carbocation ends up right where the original thing we had substituted is. That means this position is going to be more stable if there's something that helped donate electrons to stabilize that. For example, if there's a methyl group there, that's going to be more stable than a hydrogen there. Now let's do the same thing. If we want our electrophile to end up at the meta position. So we've done ortho and now we're going to do meta. So we've got our electrophile. This is the beginning of my arrow. This attacks here. This double bond attacks. And you end up with your original R group, any old substitution, a carbocation here, and your electrophile down here at the meta position. Now we're going to see the same thing. There's resonance structures to this. The proper arrow for resonance structures are double-headed like this. I tend to forget to draw them in on this kind of example. When this lone pair moves over to fill in this gap of electrons, or not lone pair, the two electrons in this bond move over to fill in this gap of electrons, then a gap of electrons is left over here, and that's why the carbocation moves. This bond hasn't been touched, and our electrophile is still at the meta position. Then we're going to have these electrons move over to fill in, and your carbocation moves one more spot. So you can see that carbocation moving around the ring. So in this case, the carbocation never ends up right where the substituted group is. So it's missing out on that. So if this substituting group is something that's donating electrons, that's not good. Because it doesn't have the opportunity to stabilize the carbocation. If this group is taking electrons away, electron withdrawing, then this is good because the carbocation never lands right where that electron withdrawing group is. So this is a good example of why ortho is favored by anything that stabilizes with the R group, And meta is favored by anything that doesn't stabilize with the R group. Now, para is actually going to be very similar up here to this one. So if we get the attack at the para position, we've got our attack, and we're going to end up with, I'm going to draw it up over here, our electrophile and this carbocation right here. This is the same position as it is in this resonance structure from before. So this electron will move and fill in those gaps. And you'll get your carbocation right on the R group. So you want to hope that that's an electron donating group, and then it'll move again and fill this in. So these resonance structures are the explanation as to why electron donating groups favor orthopara positions, because if you have an electron donating group on your ring and then it undergoes electrophilic aromatic substitution, the carbocation is going to be most stable if the attack happens in the ortho or para position. If you have an electron withdrawing group, it's going to be most favored in the if you have an electron withdrawing group, the electrophile is going to be most favored at the meta position because the carbocation never comes into contact with that destabilizing group. So that's really important for why electron donating groups are ortho-para directing and electron withdrawing groups are meta directing. These resonance structures come into play a lot. So now back to our practice problem. The question is, which of the following structures contributes to the resonance hybrid? Let me see if I can get this camera in a little bit more. It's kind of hard to get it to be at a good angle. Which of the following structures contributes to the resonance hybrid of the intermediate formed when acetanilide undergoes parabromination? So let's look at acetanilide first. If you didn't know that this structure was acetanilide, that's okay. You can guess based on the fact that it's undergoing bromination that whatever structure doesn't have the bromine there is probably going to be the structure you're looking at. So I'm going to draw that out, NHCOCH3. So it's an amide, and it's undergoing parabromination. So they're already telling you that it's going to go at the ortho-meta-para position. So your electrophile in this case is going to be Br+. This is going to attack. And we end up with, and with the lone pair H, got our oxygen like that. It's kind of drawn wonky, but I feel like this pin is a little hard to see. I might switch pins after this practice problem, but I'll go ahead and finish this one out. And we've got our bromine goes to the para position. So our carbocation's over here, and these other two bonds aren't messed with. But this is going to move around the ring. So we'll get our carbocation right here. We'll get our carbocation right here. With our double bond has moved a bromine. This was a mistake. You can ignore that. And over here. Okay, so, and then we still have our, I'm just going to call it an N with a lone pair H. And then this goes into the other one. I'm sorry, I'm running out of space. Okay, and then this moves around. And we'll have our carbocation over here, our N with the H and a lone pair, our amide up top, and then our bromine. So these are all structures that we've seen, so we know that these are all going to be present. So that's answer choice. Let's see, this is answer choice 3. Answer choice 1 and answer choice 4 are all present. So just from knowing those aromatic rings, you can probably assume that your answer is going to be E, all of these choices. However, sorry, my chair is very squeaky. However, if you choose all of these choices, you're trying to figure out what's going on here. And I'll tell you. This is an electron donating group via induction. So this lone pair can come down here and create a new structure that looks like this, where there's a double bond formed and the positive charge moves up. So not only can the positive charge be distributed all around the ring, but it can also move up into this substituent, meaning that there's one more resonance structure on top of the 3 that we already know that stabilize the para or ortho position. This also stabilizes the para or ortho position. So this is also going to be a structure. And that helps it be more stabilized than before. And that leads us very smoothly into question number 2. Which of the following contributes to the resonance stabilized hybrid formed when aniline undergoes parachlorination would be exceptionally stable? Okay, so this is basically the same question. It's showing you the para attack. So you already know the para attack is going to take place. The carbocation is going to form here and go work its way around the ring. So 1 position, 2 position, 3 position. But we know the 4th position, this comes down and stabilizes the carbocation. So this is extra, and it makes the overall product even more stable. So I think you might be thinking, well, but I thought it's not good for a low structure to have a positive charge on the more electronegative atom, and nitrogen is more electronegative than carbon. And that's true, but an sp2 carbon is closer in electronegativity to nitrogen, and this structure gives even more electron delocalization to stabilize that positive charge. So this would be the one that makes it exceptionally stable. So the right answer choice here is going to be answer choice 2. Next question. Which of these liquids would be unsuitable as an inert solvent for Friedel-Crafts reaction? Okay, so Friedel-Crafts reaction is going to involve a benzene ring of some kind. You're going to have a Lewis acid, and then either an alkyl halide or, sorry that the lighting on this is weird. I'm having to do this at home, and I know it's not ideal compared to my office, but it's the best option I have. So a carbocation is going to be formed from either of these in conjunction with the Lewis acid. And then you'll be able to get essentially electrophilic aromatic substitution. Those are the ingredients of a Friedel-Crafts reaction. So the question is, which of these would not be good as an inert solvent? So which of these will likely react? So if we have something that is electron donating, that means that this benzene ring will be more reactive because it'll have more electrons to attack the positive carbocation electrophile that's formed over here. If we have something that's deactivated with a strong electron withdrawing group, then that's going to make this less reactive, so it will be more inert. But the question is, which one of these is going to react, basically? So I'm just going to go through these and look. Chlorobenzene, that is going to be electron withdrawing, but an ortho para director. So it's slightly deactivating, but an ortho para director. It's a special exception. Nitrobenzene is going to be strongly electron withdrawing and deactivating, meta director. Acetophenone, also electron withdrawing, also strongly deactivating, meta group. Trifluoromethylbenzene. So that looks like this. You have a carbon with 3 fluorines on it. Those fluorines are strongly electronegative, and they're pulling electron density away from here, so it would not stabilize the positive charge. So I think that would be electron withdrawing and deactivating. So the only one that's even really an option would be chlorobenzene, because I think it's weakly activating because it's got these 2 competing effects. Sorry, my chair is so loud. So I think chlorobenzene is going to be your best option because it's only weakly deactivating. So it would probably react to some extent. In addition, I was going to say chlorobenzene could act as a electrophile, but I don't think that it would. So I don't think that any of these are going to react because they're strongly withdrawing. This is only weakly withdrawing. It's only weakly deactivating. And something you can do to help with questions like this is to make a list for yourself. I think I have one handy here. Make a list for yourself that goes through, okay, these groups are strongly activating because they have lone pairs that are going to be donating. These groups are moderately activating. They have lone pairs, but maybe something else. Like this has a lone pair, but it's also got a carbocation or a partial positive center here that's pulling away. These are weakly activating. They have a methyl group. They add electron density, but not a lot. And benzene is your neutral. And then let's look at weakly deactivating. So all the halogens are weakly deactivating, but they still are ortho pair directors due to their resonance structures. And then we've got some moderately deactivating groups, and then finally some strongly deactivating groups. So go through and make a list of that for yourself so that you have that handy. Okay, and then last, I'm going to try to zoom this camera in a little bit here. I feel like it's just kind of difficult to see. Lastly, the substituent deactivates the benzene ring towards electrophilic substitution. But directs the incoming group chiefly to the ortho and para positions. So that is going to be your exception. And the reason for that is because although this is strongly electron withdrawing, it does have, this is your substituent and this is your electrophile, it does have a resonance structure to stabilize the ortho para. So this is, fluorine's the most electronegative atom, so it's going to be pulling electron density away from it, but it does have one resonance structure that stabilizes the ortho para position. And it's not great. Obviously, you don't want a positive charge on fluorine, but it does stabilize it enough to where any halogen is going to be weakly deactivating due to its electrons pulling away, but will direct to the ortho para position. So normally if you have an electron withdrawing group, it's going to deactivate and going to be a meta director. If you have electron donating group, it's going to activate and be an ortho para director. This is the only exception, that it's electron withdrawing, it's deactivating, but it's an ortho para director. Halogens are the exception. Now, when I say activating, what that means is it's making it more active in a reaction. So it's adding electron density because in your electrophilic aromatic substitutions, the benzene ring is the thing attacking. So it needs more electrons. So that's why I call it activating. Okay, let's go to sorry, I really don't love this camera setup today, but I'm just doing the best with what I've got. Okay, number 5. This molecule does not normally participate as a reaction in a Friedel-Crafts reaction. So, Friedel-Crafts reaction, again, needs a benzene ring. It wants to be an activated benzene ring, so if that's possible, that's better. If it's a strongly deactivated benzene ring, it's not going to work. And then you need something that has, I'm going to call it CLX or CLR. So you either need an alkyl halide or an acyl halide. So benzene would participate. Chlorobenzene is weakly deactivated, but I think it would participate. Nitrobenzene is strongly electron withdrawing. Nitro is a very electron withdrawing group because in the resonance structure of a nitro group, there's a positive charge on that nitrogen. So a positive charge next to a positive charge is not ideal. Toluene, should have that memorized from chapter 14. It's just a CH3 group, so that's weakly activating. And then tert-butylbenzene looks like that. So it's also just weakly activating. So all these are activated, weakly deactivated, except nitrobenzene, which is strongly deactivated with a very strong electron drawing group. Because it's got a positive charge right next to a benzene ring, it's pulling away that electron density. So pulling away the electron density, I think this is the structure right off the top of my head for a nitro group. So because that's positive right there, it's pulling electron density away from the ring, and that makes the ring not want to attack your carbocation or your electrophile. Okay. For question number 6, what is the chief products of the Friedel-Crafts alkylation of benzene with 1-butene and HF? So Friedel-Crafts alkylation, I guess in this question when I said it needs a Lewis acid and then some kind of alkyl halide, it really just needs a carbocation. So in this case, if we have butene, 1, 2, 3, 4, and it's a double bond, so right here, and HF, this is going to generate a carbocation. And we've seen this from reactions with alkenes in an earlier chapter. So a positive charge is going to go here, and a hydrogen would form right here. That's an implied hydrogen, so I'm not going to draw it in the future. Now, if you have this carbocation and your benzene attacks, so this is the electrophile, your benzene's attacking. It doesn't matter where the benzene goes or where the alkyl group goes because it's a symmetrical compound because benzene is, any of these are all the same. So let's see, it forms a bond right here. 1, 2, 3, 4. And then on the other side of that double bond, there's going to be a positive charge. Now, the resonance structure goes all the way around, but in this case, we're going to restore aromaticity. This fluorine is probably going to come steal the other hydrogen that's left behind here, or something similar. And that's going to happen pretty quickly because benzene rings want to be aromatic, so it doesn't like having that carbocation, and you'll restore with your final product. This basic reaction, an electrophile is formed, benzene attacks the electrophile, and then aromaticity is restored, is going to be your formula for every electrophilic aromatic substitution. So let's see, which one of these is the right answer? So we should draw all these out. Butylbenzene would look like this. 1, 2, 3, 4. And the reason that one's not right is because you're forming a carbocation is not going to form on the primary position. It's always going to go to the more stable. So it went to the secondary position, so that's where this attaches. 2-phenylbutane. Okay, so butane is the main one. 1, 2, 3, 4. 1, 2. Actually, that looks right. 2-phenylbutane. I think that might be our right answer. 2-methyl-1-phenylpropane. So let's do propane. 1, 2, 3. 2-methyl, 1-phenyl. That does not look like what we have at all. Tert-butylbenzene. Tert-butylbenzene looks like, can you see me over there? Like this. It's a cross. And then 2,2-diphenylbutane. That's 2 phenyl groups. We don't have 2 phenyl groups, so that's not going to be right. So I think our right choice is answer choice B. Okay, number 7. A mixture of chlorobenzene and anisole, you should have that memorized from the last chapter. Mixture of chlorobenzene and anisole is allowed to react with Br2 in the presence of trace amounts of FeBr3. What is the principal product of the competing reactions? Okay, so this is going to be a bromination reaction. So you should know with all the electrophilic aromatic substitutions, there's halogenation, there is Friedel-Crafts alkylation, that's where you add an alkyl group. There's Friedel-Crafts acylation, that's where you add an acyl group. There's sulfonation, nitration. I can't think of any others off the top of my head, but it's listed at the beginning and end of your chapter PowerPoints. So check those out and Make sure that you know all of these and what substituents they require. So for halogenation, you're going to need a halogen and you're going to need a Lewis acid. For Friedel-Crafts alkylation, you're going to need some way to form a carbocation. You're going to need a Lewis acid, and you're going to need a benzene ring, preferably activated. For Friedel-Crafts acylation, you're going to need an acyl chloride, you're going to need a benzene ring, and you're going to need a Lewis acid. For sulfonation, I think you just need H2SO4. And for nitration, you need H2SO4 and HNO3, both of those with a benzene ring. So you need to know those and recognize those. So when I see Br2, FeBr3, and some kind of benzene ring, I know that that's going to be a bromination. Now the question is, which one of these benzene rings is it going to react with? This is see if you can quiz yourself before I say it. Is this activating or deactivating? And then what about for this one? This is going to be weakly deactivating. Remember, it's one of those exceptions. It's probably going to react some with this reaction, but not as much as something that's weakly activated, or that's activated. This one actually I think is moderately activated. So this is an electron withdrawing group, but it's the special exception that's orthopara. This activating group, it's not an exception, it's electron donating, and it's also orthopara directing. So if I'm having to choose which one of these competing reactions is going to go first, I'm going to choose the activated group. And your bromine is going to go to the orthopara position. So I'm going to draw it down here so you can see it more easily. You're going to have your ortho position, or it could be at the para position. Or honestly, if it's strongly activated, it could go to multiple locations. But they usually won't give you both of these as competing responses. So all these look like there's one bromo, and we know it's not chlorobenzene because it's not as activated as anisole. So just knowing that, you can narrow your answer choices down to D or E. Then you just need to know, is it going to go meta or para? So let's see, 1, 2, 3, 4. So 4 bromo anisole. Meta would have been 3 bromo anisole, and that's only if this would be an electron withdrawing group. And if it was an electron withdrawing group, it would not have gone as quickly as this electron donating group. Okay, next question. This looks like an alkylation. So for all of these, we have plain old benzene, and then we have something that's combined with an acid to turn into an electrophile. So this is actually mostly a review of an earlier chapter for you guys. It's just a review of reactions of alkenes. So I'm going to go pretty quickly. CH2 with a double bond to C. Okay, it looks like this, and it's reacted with H+. So the double bond is the nucleophile. This is the electrophile. Your proton will go to the outside, and you'll get a positive charge because 2 electrons go into forming a bond with this proton. So then there's nothing left behind here. Carbon's missing a bond. So it's a positive charge right there in the middle. And then when benzene attacks, it'll attack at the carbocation, and there's 3 methyl groups coming out of that. So that looks like tert-butylbenzene to me. So A will definitely work. B, let's see, CH3 off of a carbon with an alcohol. Okay, so this is your structure for answer choice B, and you also have an acid with it. So in this case, this is a reaction of, this is basically an elimination, the first step of dehydration, I think, actually. So this would, another review, I just had to remember which chapter it was from. So you'd get your OH2 plus, and then your leaving group would leave. So maybe technically this is the first step of an elimination reaction. This is a single bond. I just drew it crazy. And now your benzene will attack, and it's actually going to attack this, and this is the same structure. I just drew them poorly. It'll attack. It'll end up forming an uranium ion originally. So first it will have that plus a carbocation, and then aromaticity will be restored. And you'll end up with your same tert-butylbenzene. The same thing is going to happen here. This will attack, and you'll get an intermediate step that I didn't draw. because it happens so quickly. I sometimes forget to draw that, but that's not a good excuse to leave it out. That looks like this. And then there's a proton left behind here, and that proton will be taken away, and the electrons from it will fill in this gap. Okay, and then last but not least, we have this structure with AlCl3. It's going to act very similarly to this, where it'll form a complex with the AlCl3, and then that will leave. And you'll get a positive charge left behind, and this looks exactly the same as the other one, so it's going to go exactly the same as the other one. So the answer choice is actually answer choice D, all of these choices. Okay. Next question, question number 9. Consider the following reaction. What is the expected product? Okay, so we have a strongly activating group. It's got a lone pair there, so you know that it can participate in resonance, and a weakly deactivating group. So if I had to pick between these, I think this would be the stronger effect because it's strongly activating, whereas this is weakly deactivating. So that means that your substitution is going to go to the ortho or the para position. Well, the para position is taken, so it's going to go to the ortho position. So I think they're missing an FeBr. I think some kind of acid would help this. I'm not sure, or even an H+. Anyway, so we'd first have our partially positive, our bromine electrophile, and that would attack and break the bond between the two Brs. And then you would get a substitution. I think you would have to go at the ortho position because the para position is already taken. So let's see, then we've got our positive charge right here, and then it would go all the way around the ring. Now, if you have that in excess, it will react twice. So because this question says what is the expected product, I think it's saying because this is activated, it's going to react multiple times with the excess. So you're going to end up with 2 substitutions at the ortho position. However, I would also say that if it just said what would be the products, this is also a viable option. Now, you can eliminate and get this down to 50-50 just between these two. If you know that NH2 is an ortho para director, it's not going to direct to the meta, so that's not going to work. If you know that NH2 is an ortho para director, not going to direct to the meta, that's not going to work. And here, the chlorine has swapped with the bromine. That would be crazy. So you can eliminate all 3 of these and get it down just to these 2, and between these 2, I'd say this is the better answer. I am surprised a little bit that there's not a Lewis acid on there. That would be my suspicion, is that it should have been included. I just now noticed this. I didn't notice when I was preparing, so you might check with your professor just to make sure. Maybe I'm missing or forgetting a practice problem or a type of reaction from these, so just maybe check in just in case. Which of the following reactions would produce isopropyl benzene? This is going to be very similar to the last question. All these are reacting with benzene. Not the last question, I guess. Question before last. Question number 8. All these are reacting with benzene in the presence of an acid, so we're just trying to make an electrophile. So in this case, if your chlorine formed a complex with AlCl3 and left, this carbocation is not viable because it's a primary carbocation. So it's going to undergo rearrangement, and it will react from this position. The benzene will attack, and then aromaticity will be restored, and this will be your final product. So that is isopropyl benzene. In this case, you have an alkene, propene, with HF. This will act as your electrophile. This bond will break. The positive charge is not going to go here because it wants to be more stable. So the positive charge will go here, and there'll be an implied hydrogen on the outer carbon. And then the same thing will happen. The benzene will attack, and then aromaticity will be restored. A very, very similar situation here. your OH group is going to be protonated to make OH2, also known as H2O, which is a good leaving group. So that would leave. It would take a long time to get that slow step to take place, that leaving group leaving. And that would leave a methyl carbocation. It's going to undergo rearrangement almost immediately, and you'll end up with this. And then with the halogen, with the AlCl3, it'll form a complex with the AlCl3. I don't think you need to know the mechanism for that. You may want to check and make sure. And this bond will break, and you'll end up with a carbocation. So you have the same carbocation in all of these situations. And so they all undergo the same reaction with benzene, and they all produce isopropyl benzene. So the answer is all of these. Which of the following reactions would give the products indicated in substantial amounts, i.e. in greater than 50% yield? Okay, so in greater than 50% yield means it's going to be a pretty stable reaction. So we have an activated benzene ring for all three of these. So, well, this is neutral. It's not activated, but it's not going to eliminate it necessarily from contention. But if we have a methyl halogen and it forms a complex with the AlCl3, this needs to leave to form CH3 plus with AlCl4 minus. But do we ever see a methyl carbocation? No, that doesn't work, and that would not form. Same thing here. That doesn't work, and that would not form. Neither of those are going to be reasonable. Even if they were reasonable, it wouldn't go to the meta position. It would go to the ortho position. So not reasonable. This last one, that carbocation could form initially. So we'll draw it out like this. As the chlorine, it's going to form a complex with the AlCl3. This bond will break. And you'll end up with a partial positive here plus AlCl4 minus. This would immediately undergo rearrangement to look like what we saw up in the last question. And then it would not give you this chain. It would give you isopropyl benzene. So the answer is none of these choices. Okay. For answer choice number 12. For answer choice 12? I'm very tired. It's late at night right now. For practice problem number 12. What is the major product of the following reaction? So this is a Friedel-Crafts acylation. You can spend a lot of time trying to figure out the mechanism of the formation of the electrophile. I generally just say this chlorine will form a complex with the AlCl3. This bond will break, and you're left with a positive charge here and AlCl4 minus. I don't think you need to know this, although you might. There can be the formation of a triple bond here, where this comes down and fills in. And then the positive charge is up here. I don't think you'll need to know that. But just in case, you might want to go check it out. I'm not sure how involved this is. But ultimately, I think of it in this position. Then the benzene ring will attack here. And you'll end up with an acylation. So that's an abbreviated mechanism. I'm not going to go through the whole mechanism for you right now because you can look it up in your textbook or your class notes pretty easily, but this is how I think of it to make a shorter mechanism. So the chlorine leaves with AlCl4, and then the benzene just tucks the electrophile right there at that partial positive. So that's not 100% accurate, but it is a good way to think about it. So that's what we're going to get. And now the next question is, where will it go? Will it go on this ring or that ring? Both are benzene rings. One, however, is activated because it has a methyl group, and the other is deactivated because it has a carbonyl group which has a partial positive right here, which is pulling electrons away. So, and the way you can look at that is just cover up the other ring. Is this activated or deactivated? It's got a methyl group, so it's weakly activated. Now cover up this side. Is this activated or deactivated? It's slightly moderately deactivated at least. I don't have it off the top of my head, but it's going to be pulling those carbocations away. So if I had to pick one, I would pick the ring on the right. Then we have to ask ourselves, is it going to be ortho-para or meta? Well, if it's activating, and it's going to be ortho-para. So you can either get your carbonyl carbon here, or ortho-meta-para on directly the other side. So I'm looking for something that has it at either one of those positions. This is on the deactivated ring, so that's not right. This is on the deactivated ring, so that's not right. This is on the deactivated ring, so that's not right. Just knowing which one is activating and which one's deactivating helps you narrow it down that much. This is at the meta position, so it has to be at the para position, so that's right. Okay, question number 13. I love questions like this. First things first. You should have this memorized from the previous chapter. SOCl2 is going to turn an alcohol or a carboxylic acid into a chlorine. Then we have the hallmarks for a Friedel-Crafts alkylation, AlCl3. So when I think of that, I think of a complex forming between these two, and then this lone pair, this double bond. What am I thinking? It's too late. This single bond right here breaking and leaving behind that carbocation, just like we talked about up here. Then I think of the benzene attacking and forming. First, it would form a carbocation, the uranium ion, and then the aromaticity would be restored, and you'd end up with this structure. So the first one created this chlorine. The second one, Friedel-Crafts acylation. So that leaves us with this. This is, I can't remember off the top of my head if it's Wolf, Kishner, or Clemenson, but it's one of those, and it's a reduction. And I love these because literally all they do is delete that carbonyl bond. They just take it away. If you have a carbon double bond to an oxygen, both the Wolff-Kishner and the Clemenson reduction just eliminate it. So I just scribble it out. And that's what we're looking for. And it looks like the only one that looks like that is answer choice E. If you just recognize this step, then you'll know there can't be any carbonyl carbons left behind, so you could at least eliminate these two just from having memorized that. All right, now let's look at question 14. Okay, so this goes back to knowing your electrophilic aromatic substitutions. What would you expect the major product to obtain from the following reaction? So I see nitric acid and sulfuric acid. I know that's going to add a nitro group. All these have a nitro group added, so then we just have to decide what's the position. So go back to your old standby. Cover up the ring. It's got a carbonyl carbon. That's a partial positive. That's pulling electron density away. Now cover up the ring. Cover up this ring. You have the carbonyl carbon pulling electron density away. Cover up this ring. You have a lone pair here. That's donating electrons. So between the two, we've got basically acetophenone. That would be pulling it away. And here you have an amine that's donating electrons. So this ring is going to be where the reaction happens. Anywhere there's a nitro on the deactivated ring, get rid of it. It's the exact same type of problem as practice problem 12. Now we've narrowed it down to these two rings. And if this is activated, then we know it has to be ortho or para. So it's going to be para. Ortho, meta, para. Okay, 15 is a different type of reaction. It's a radical reaction. And you should have learned those, I think, in chapter 12. But this is kind of actually just showing you that with aromatic rings, there's a new most stable position. So before we saw that the radical would form in the most stable position, and that's where your bromination would go. Well, in this case, the most stable position is right here because it's in resonance. So because it's in resonance, that's going to be where your radical forms, and that's going to be where it forms a bond with bromine. So Anytime you have a bromination reaction with a benzene ring, an allyl, or tertiary, that's where the bromine's going to go, at the most stable of these. So in this case, I think the most stable position is here, so you're going to have a bromine that adds in right there. And that's answer choice D, I guess, 4. And in this reaction, if you're not sure or confused on the mechanism of radical reactions, are actually pretty straightforward. My students don't usually have trouble with them, but you can go back to chapter, I really think it's chapter 12 or 11, and they go over these, and they're pretty straightforward. Okay, next question. Arrange the following compounds in order of decreasing reactivity and electrophilic substitution. Okay, so when I'm thinking, and it'll really help if you make your list, but when I'm thinking, I always put benzene as the neutral. And benzene isn't an option here, but I just put it as the neutral. Bromine, we know, or any halogens, are weakly deactivating. So I'm going to say weakly deactive. Strongly deactivating, we know nitro groups are strongly deactivating. That one's just one that it's easy to memorize. Methyl groups are slightly activating, so I'm going to put them on this side. And actually, because of the lone pairs right here, this one also is activating, more so than a methyl group. Anisole is what this is. And then acetophenone has a partial positive right there because there's a resonance structure where there's positive here and a negative charge up here for carbonyl covalents. That's going to come in a lot more in the later chapters, but just knowing that now knows that it's electron withdrawing, and it's not as electron withdrawing as nitro, I don't think, so I'm actually going to put it in the middle here. But I'm not, I could go back and forth on this one. I don't have it in the top of my head. So the way I would approach this problem is I don't have that memorized, but I think these are comparable. I'm going to go with nitrogen first, then nitro group first. Now let's look at our answer choices. Are there any we can eliminate right away? Well, we're going in order of decreasing reactivity, so the most reactive needs to come first, and that's going to be one that has the most electrons donated to it. So because these are the attacking groups, so they're going to be the most reactive when they have more electrons. So that is answer choice 2. So I'm going to eliminate any that don't start with the most reactive. Boom, and I've got my right answer. It didn't even matter that I wasn't sure between these two. So that's something that you can do, a test-taking strategy. Do the best you can. Use the information that you already have to work through your practice problems. Okay, so for question 17, again, we're going to go to the most stable position. That's going to be the benzylic, allylic, or even the tertiary position. Those are ones I'm looking for. Benzylic, allylic, looks like this, and tertiary. That's a tert-butyl. I'm struggling. It is too late at night for me to be doing this. So any of these positions are going to be the most stable. There's a benzylic position right here, so I'm going to assume that's where the chlorine is going to go. So the only one with an answer choice that has that is going to be answer choice E. To get a chlorine at these positions, you need to do what? Do you know it off the top of your head? It's FeCl3 and Cl2. And it's only going to go, this is a good way to test yourself. If you're looking at this is slightly more activated because it has the benzene and the methyl, only slightly. Both of these are going to be pretty reactive. And then look for your ortho, meta, para. So it'd probably go maybe right here or ortho. Yeah, probably right here because it's para one and ortho the other. So that's a good way to test yourself. Okay, this is how I get this chlorine, but how could I get any of these? Toluene is subject to the action of the following reagents in the given order. Okay, the first one. We talked about this briefly in the last chapter, but did we talk about this? Yes, in the oxidation and reduction chapter. KMNO4 will turn anything off of a benzene ring into carboxylic acid. That's just one that it's easy to memorize, and then you'll know it. So just memorize that. KMNO4 does all kinds of stuff. This is just like kind of a random side review. If you have KMNO4 that's cold and dilute, it will add an alcohol to two sides of a double bond. If you have KMNO4 that is hot and concentrated, it will actually split your double bond up into two ketones, like this. And if you have KMNO4 with a benzene ring with any kind of R group off of it, there's a few exceptions, it will turn it into a carboxylic acid. Okay, and then let's see, what's our next step? A nitric acid and H2SO4, that's going to be nitration. This is electron withdrawing, so I think it's going to go to the meta position, ortho-meta. So I think we're going to have this, ortho-meta. And then we have Br2 and FeBr3, so that's a bromination. So you should memorize those so that you know them off the top of your head. Now this is a very deactivated ring, so I actually think it would be very hard for this last reaction to take place. But saying that it did, it would give a bromine meta these. So ortho-meta, ortho-meta. Both of these meta positions happen to be right there, so I think this would be your best bet. But you do have to kind of solve the puzzle of like which one's the strongest activating, deactivating, where is it going to go ortho-meta to? But in this case, you don't have to because it's meta to both of these when it's in this position. So that means your right choice is going to be answer choice A. Okay, and then our very last page, question 19. So the first step, we've got a benzene ring, something with a halogen, and AlCl3. This is Friedel-Crafts alkylation. So be sure you recognize that when you see it. If it had a acid chloride group or an acyl chloride group, that would be Friedel-Crafts acylation. So a complex is going to be formed with the AlCl3, and then this bond is going to break, and you'll get a carbocation plus AlCl4 minus. So this is what you end up with. That's a plus, not a positive. And then this is going to attack. Your benzene will attack to form this structure. And originally there will be a carbocation, but aromaticity will be restored. I usually skip that step, but it's not a good habit to do that. I'm sorry. So the intermediate would look like this. Nope, I always just draw that thing there with the positive charge right there. And then there is still a hydrogen here. The lone pair from that hydrogen that gets left behind will go and restore the aromaticity. That's a very small drawing, but I hope you are tracking with me. Okay, so then the next step is NBS and peroxide. So this is a radical reaction. So it's going to go to the most stable position. And the most stable position is the benzylic or allylic position. So that's right here. So that's where our bromine will attach. Okay, and then the next step is sodium methoxide, methanol, and heat. And I don't know if you recognize this, but I hope you did because we drilled it into your mind. This is an elimination reaction. It's an E2 reaction. You got a strong nucleophile. And it has two options. It can form a bond here or a bond here. Well, if it formed a bond here, this carbon would have 1, 2, 3, 4, 5 bonds to it, which is not possible. So it has to form a bond on the other side. Luckily, this is symmetrical, so either way, it's the same. If we put it up here or down there, it'd be the same compound. Then with MCPBA, I don't know if you remember that, but that makes an epoxide. So this is a fun multi-step problem where you're putting it together all the things that you've learned from the past, and this kind of practice problem will help you in your preparations for your final. And then for CH3, then we add in CH3 MgBr. That's a Grignard reagent. I think of Grignard reagents as equivalent to a carb anion. So that'll attack, and it's going to attack base least, acid most. So the least substituted side, because this is base catalyzed, because this is a base. So it'll attack and open this ring up. Oh, I drew this at a bad angle. Can you still see? Yeah. Okay. So we're going to have our ring opened up. So because the ring opened up, there's an O minus here. And the new CH3 group has attached right there. Okay, and then you put that in acid, and you end up with a benzene ring with a cyclohexane ring with an alcohol and a methyl group. And the only one that looks like that, it looks like, is this one stops at this step and adds a methyl out of nowhere. This one looks right to me. I'm going to go with answer choice B for now. Answer choice C is wrong because the methyl and the alcohol can't be on the same position. Oh, you know what? I made a mistake. Answer choice B is not right because the methyl group is right at the alcohol group is right at the joint where the cyclohexane meets the benzene, and I had it one away, so that's wrong too. So I think answer choice D is actually right. And answer choice E would be right if it was acid catalyzed epoxide ring opening and attacked the most catalyzed side, but because it attacked the substituted side, but because it attacked the least substituted side, that's not the right answer. And last but not least, which of the following carbocations would be most stable? Much like radicals, these are our most stable carbocations at the benzylic, allylic, and tertiary position. Oh, the same thing. So this one, there's a benzene, and it's all the way at the end, so as a primary carbocation, so no way. This one is a benzene on this side. It's a tertiary carbocation, so maybe. This one has a benzene on this side. It's a secondary carbocation, not as good as this one. This is a benzene on this side and a carbocation at the benzylic position. So I'm going to go with answer choice E. So that's it for this round of practice problems. I hope you guys found this helpful. I'm sorry the lighting wasn't great. I had to do it in my home office instead of my office at work, but hopefully this is still helpful for you. And if you have any questions, please feel free to email me. Thanks. Good luck studying for